Hi, so in this video, I'm going to be talking about an interview question called branch sums, right? So branch sums is basically the concept or the interview question which can be related to binary trees. And as you can see here that we have an input consisting of various nodes, right? There are numerous nodes and you can kind of depict this as a graph, but as of now in the interview you will be given a root node and the root node as of now is 1, right? So the one which is the root node will be given to you and you have to be returning an array. As you can see, we have an output here, right? So you have to be returning an array which will be consisting of the branch sums. So let's just get familiarized with what actually branch sum is. So a branch sum is basically the sum of all the node values, right? Sum of all the node values from the root node till the very end. And what is the very end? What do I mean by the end in a tree? So the end I'm talking about here is basically the node which has no children. So what are the nodes which have no children here? So the nodes which have no children are 8, 9, 5, 6 and 7. Apart from 8, 9, 5, 6 and 7, all of them have children, right? Also, this is a binary tree. So binary tree is a tree which can have at most 2 nodes or 2 children, which means that it can have 0 children, 1 children, 2 children, but not 2 or more, right? So it cannot have, for example, 3, 4, 5 and then so on, right? And I hope that makes sense. So basically, we have to be calculating or computing the sum of all the node values or the node data from the root node till the very end, which is nothing but the leaf nodes. So just consider this first branch here. So the first branch I'm highlighting with, maybe I can just highlight this with the marker, that will really make sense. So this is the first branch here, right? So this is the first branch, 1, 2, 4 and 8. What is the sum of all the node values? 8, 4, 2 and 1. So 8 plus 4 is 12, 12 plus 2 is 14 and 14 plus 1 is 15, and therefore we have 15 as the first input or the first output in the array, right? Let's consider another branch, right? Let's consider the second branch here. So the second branch is 1, 2, 4 and 9, right? 1, 2, 4 and 9. What is the sum here? So it's 9 plus 4 is 13, 13 plus 2 is 15, 15 plus 1 is 16, and therefore we have 16 here, right? Let's consider the third one. So third one is 1, 2 and 5 namely, and the sum is 8, and therefore we have 8 here, right? And I'll just go through them one by one so you can kind of imagine them or figure out what's happening here really. So 6 plus 3 is 9, 9 plus 1 is 10, therefore we have 10. Let's consider the last one here, and I think you all are smart enough to figure this out already. So this is going to be 7 plus 3 is 10, 10 plus 1 is 11, and therefore we have 11, right? I think that makes sense and we are on the same page. Now to compute this, right, how do we do that? Well, I'm going to be maintaining an array, right, which I can kind of call that as sums array, right? So I'll just write sums, right, and this is going to be empty at the beginning. And then I'm going to be maintaining maybe 2 variables, right? So the first variable will be current sum, so current underscore sum. You can kind of figure this as current, right? So I'm just writing it in short, CURR. So current sum is initially 0, right? And new sum, right? So new sum I will be maintaining. New sum is also basically 0, right? As of now, new sum is also 0. And then I'll be recursively calling, and I'll be using the concept of recursion, right? I'll just explain that what's happening. Recursion. So these are all of the main important things which are going around, right, when I'm trying to compute the branch sums as mentioned by the interviewer. So currently I'm at the root node. So root node will be given to you, right? So root node will maybe 1, 2, 3, 0, whatever the case may be. So root node will be given to you, right? And you have to definitely compute or complete the function, right, as and when asked. So when I'm at the root node, my current sum, so as of now I'm representing the current sum as CS, right? So current sum is 0, right? So when I'm at the root node, what will be my new sum? So let's suppose new sum is NS, right? So new sum will be the node value, which is 1, plus the current sum. So that's 1 plus 0, which is 1. So therefore new sum at the root node 1 is basically 1, right? We are good to go. Now when I'm at a particular node, what I'll do is I'll recursively call the left and the right child, right? So just to explain the example, right? This is a very simple question. No need to worry about. So just to explain the left part of the left aspect of this code, I'll just try to explain 1, 2, 4, and 8, right? And then you can kind of figure out the entire stuff. So I'm recursively calling to the left side as of now. I'll also recursively call to the right side, but let's just consider the left side first. So I'm recursively calling to the left side. So at 2, my current sum, okay, my bad. So my current sum will be basically new sum as of now. So that's 1, right? And my new sum will be current sum, right? So current sum plus the node value, which is 2. So this should be what? 3, right? So 2 plus 1 is 3. Again, I'm recursively calling maybe to 4, right? So what will be my new sum here? So my new sum will be my previous current sum. So basically up here at the end, my current sum is reinitialized to new sum, right? So that's how it's getting computed or swapped, right? You can kind of figure that out as well. So new sum will be current sum plus the node value. So my current sum was 3. So 3 plus 4 is 7, right? So my new sum is 7. What will be the new sum at 8? So my current sum as of now is 7. My new sum will be 8 plus current sum, which is 8 plus 7, and which gives us 15, and therefore we have 15 in the output array. But how do I understand that I have to end the process here, or I have to append to the array, right? So here's the base case comes into play, right? So here's where the base case comes into play. Since I mentioned that we are using recursion, so I'm just going to be explaining 2 of the base cases in a very simple manner, right? So for example, this is my current node, right? And it has left child and the right child, right? So L and R. So this is my first case. Let's consider a second case, right? So my second case will be, this is my current node and it has no left and right child, right? It has no left and right child. I think that's good to go. And we have a third case, right? We have a third case where the current node is there and there is only one left child and there is no right child, right? There is no right child. Or it might be the case that there is only one child, which is the right child and no left child, right? So either ways, right? It can go either ways. So let's just consider the left child, right? As of now. So these are the 2 cases which in fact 3 cases which you can end up with, right? So you can end up with, so for example, if you are at a current node, you can have left and right children, or you can have 0 children, or you can have only 1 children, right? So how to handle these 3 cases, how to handle them, right? So let's see. What I'm going to be doing is basically defining the base cases or writing the base cases at the beginning of the recursion, just to make sure that we are handling them. So what will happen here, right? So what will happen in the first test case or in the first base case or the condition? So in this case, I'm just going to be simply passing it, right? So simply pass. There is no need to return up at any point up here, right? I don't need to return at any point here because we definitely have left and right children. Therefore, there is room for more exploration, right? Let's consider the second case. In this case, I can see that this is the leaf node, right? So for example, current node can be 8, 9, 5, and then so on, whatever the case may be. So I can see this is the leaf node because it has no children, right? So in this case, how I can handle this is I can just write that if the current node has no left and no right child, right? In this case, I'm going to be appending, right? So in my sums array, I'm going to be appending the new sum value, and then I'm just going to simply return. As simple as that, right? So what is it really checking? That if current node has no left, right? So it has no left child and no right child, so it has no right child, then simply return, right? And before returning, I'm definitely appending the new sum value to my sums array so that when I print it at the end, I have the values retained, right? Let's consider the third case here, right? What will happen really? So when the third case kind of hits the second base case here, so it checks that if current node has no left, but it has left child, right? So what it will do, it will pass, right? And in recursion, I'll call, so I'll just write it properly. So in recursion, I'll recursively call the left part, and I'll recursively call the right part, right? And when again the function kind of computes, right? So this is the function maybe for both of them. So in this case, the left child will simply be matching the case where this one, right? So my left child, when I'm at the left child, I can see that this is matching this case. It has no left and no right child, right? There is no left and there is no right child. So this kind of passes. This function kind of computes, right? So this is going to be returning something, right? But how do I handle the right case? When current node is recursively calling to the right side, we are kind of seeing that there is no right child, right? So how do we handle that? So basically by default, we have the value none if there is no right child, right? Or the left child. So in this case, we have no right child, therefore value is none. So in this case, I can just consider that if root is none, then or if root, or you can kind of interpret this as current node. So if current node is none, then simply return and nothing to do, right? So these are all the base cases which you have to handle, and they are pretty much 2 in number, right? So I think we can get started with the coding part, right? And I'll try my best to quickly make the tree here. So if name, I'll just write the prerequisites here. And one more thing, that I'm writing the code in Python here, so you can kind of convert them into Java, C++, C, or whatever your language preference is, because you can kind of already know that Python is a human readable language kind of a thing, right? You can easily understand and convert it into your language of own choice. Okay, so I'm going to be defining one object here. So for example, my object is a root, right? Oh, my bad, this should be root, and I'll be defining this object. I'll be assigning this object to a class called binary tree, right? So binary tree, and my root node is basically having a value of 1, right? So I'll just write quickly, so class binary tree, right? And then I'll be defining the constructor here, and I can see here that I'm passing one value here, right? So that's the node's value or the node data, right? So I can just write value. Some people like to write instead of value, some people like to write it as data, and that's not wrong at all, right? So you can go with value or data, whatever the case may be. I'll just write self.value is equal to value. So basically self in Python kind of binds the objects of the class together. That's it. Nothing that's about self on a higher level of view. So binary tree has basically 3 properties, right? The first one I've written, it's value. The second one will be the left child. So self dot left underscore child. I mentioned that I'm using none here, right? In your case, you can use -1, you can use false, you can use true, you can use maybe a value like NA, right? A string kind of a formation, but it really doesn't matter. You have to be sticking with it. So for example, if I have a left child as this thing, right? None, and I have a right child as maybe like -1, then it's fine, but it kind of dismantles the whole orientation, right? It kind of dismantles it. So I'll just go with stick with the original one, right? So it's none as of now. So I'll just quickly build the tree. So my tree root dot left has a value of, let's see, it's 2, right? I'll just explain what I'm writing. So tree root dot right, okay, it should be right child, and I think I should correct up as well. So this should be left underscore child is binary tree 2 and binary tree 3. So what's really happening, or what am I doing here? So tree root is binary tree 1, right? Okay, my bad. Tree root is binary tree 1, right? So my root is as of now is 1, right? So root as of now is 1, or tree root, right? So I'll just write root tree up here because I have no space here. So root tree, right? So I'm writing that root tree dot left child, right, is 2. That's what's happening. So once the one which is assigned to the root tree, so root tree dot left, what is the left child of 1? So that's 2, and that's what I'm writing. Tree root dot left child. So okay, my bad. So tree root dot left child is having a value of 2. So I'm kind of declaring it as 2. Tree root of right child, right? So the right child of 1, right, is 3. As simple as that. Let's get further. So I'll just try to copy this thing. Control V, and then I can just write it again. Yeah. So I'm just continuing with the construction for the node value with the node value 2, right? So 2 is having a left child of 4 and 2 is having a right child of 5, right? So left child dot left child, right? So left child, and it's going to be 4 as of now, and this should be 5. So left child dot right child, right? And then again I'm just going to be copying this entire stuff, right? So control V. So right now I'm at the node value 4, right? So 4 is having a left child as 8 and right child as 9, right? So what I'm going to be really doing is, yeah, I'll just try to write it once again. Yeah, so I am currently at 4, right? So left child, so left child once more, and then we will have 8, and this might be seeming confusing to you, so I'll just explain that again with respect to any one branch. Okay, so right child. Okay, and I think we have covered 1 2 3 4 5 8 9 6 and 7 are remaining. So 6 and 7 are assigned to 3, right? So I'll just pick the third one. Yeah, third one is up here, so I'll just pick the third one, and then maybe like try to write this entire stuff here. Perfect. So as far as the third node is concerned, so right child dot left value is how much? So my left value is basically for 3 is 6, right? So it's 6, and the right value is 7. Okay, so I'll just write right child dot right child. Okay, perfect. Now you might be wondering what's written here. It might seem confusing, but again, this is something which you don't really have to write in the interview. You will be given a function with the tree root or the root value, and then you have to compute it, which is kind of easier, right? I'm just writing it to make the formation of tree here. Okay, so maybe like consider this one 8 1, right? So what have I really written here? Notice how many left childs are there, right? Tree root dot left child dot left child dot left child. So it's 3 times, right? And what is the value? It's 8. Let's see the diagram. Up here you can see we have the root value 1. So 1 dot left child is 2, dot left child is 4, dot left child is 8. So how many times? 1, 2, 3. 3 times, right? Let's consider maybe 6. So what should be it? It should be tree dot right child dot left child, right? So let's consider 6. Where is 6? 6 is here. So tree dot right child dot left child. So that's how I am making the tree here. Okay. Now maybe I can just write here answer, right? So my answer will be an array which I'll be getting from a function. So maybe get underscore answer, right? That's my function here. What should I be passing here? So I will be passing my root value, which is tree underscore root. Instead of tree underscore root, you can simply take it as root. That's not a restriction here, but I've just used it randomly, right? And then at the end, I'll just print answer. So I hope that makes sense. Let's quickly define the function here. So define get answer function. So get answer, and it's having a value of root here, right? So my output should be an array, right? An array. Okay, let's see. So sums output, right? Or maybe like branch sum output, right? It's an empty array as of now, right? Because that's where I will be storing the answers, right? And maybe like my current sum, right? So my current sum is 0 as of now, right? I can even write the cumulative sum or the previous sum. Okay, wait, I have been using current sum, right? I've been using current sum and the next sum, right? Kind of like that. Okay, let's see. So basically, oh, not next sum, but new sum, right? So I've also been using new sum, but again, this is going to be something which I'll be implementing in the next function, which I'm going to write in a moment. Okay, so current sum is 0 as of now, right? So I'm just going to be returning the branch sum output, right? So I'll just return the branch sum output because that's where the answer will be stored, right? And how should I be storing the answer? I'll be calling a function called maybe like branch sum compute, right? And what are the main parameters, right, I should be passing here? So maybe I can pass the root value first, right? Root value, and then the current sum here, right? So current sum has been passed, and then I'll be passing my array, right? As simple as that. Let's just quickly write the function here. So it's basically going to be define branch underscore sum underscore compute, right? it's having value as root current sum, right? So it's going to be current underscore sum, and then branch underscore sum underscore output. And I'm pretty sure I've made spelling mistakes somewhere. If not, then we are good to go, right? So now that we are done with this, I'll define my base cases here, right? So what were the base cases here, right? I'll just look up the board. That's not an issue. So the base cases up here were as simple as that if root is none, right? So if root is none, then simply return, right? So this is my base case 1. And again, I have explained why we are validating this base case and how it's going to be helpful. So if root is none, right, or I can just simply write it in capitals, none, then I'll just simply return, right? That's not an issue. Now I'm going to be computing my new sum here. So new underscore sum. And what was the formula I was using here, right? So the formula up here I was using was basically my new sum, right? So my new sum was current sum plus node value, right? So node dot value. That's how I'm computing the new sum, right? So I'll just write new sum is equal to current sum plus node value. What is the node here? It's basically the root, right? So root dot value. And why have I written value here? Again, value is going to be storing the node value or the node data, whatever you may call it, right? Now that my new sum has been computed, I'll check that if I'm at the I'm at the leaf node, right, where there is no children. So this is my base case 2, right? This is my base case 2. I'll check that if, again, this is something I have defined here already. So I think I have defined up here. Yeah, this is it. So if current node has no left and no right child, right, then I'll just append the new sum to the answer and then return, right? As simple as that. So if root dot left is none and root dot right, in fact this should be right child, right, is none, I'll just correct this up here as well so that we are on the safer page, is none, then basically I'll be appending the answer, right? So branch sum output dot append new sum, right? Or this should be new underscore sum. And let me just check with the left and the right child declarations. Yeah, they are completely fine. Okay. Now that this has been done, I'll just simply return, right? There is no point further going because this will be resulting in a stack overflow, right? Now I'll be recursively calling the left and the right child, right? So I'll recursively call the left and the right child, right? And I hope the recording is in process. That's not an issue. So how do I do that? I'll just simply write the function name, right? So branch sum output. And what should I be doing in the next step? Well, if you noticed here from the explanation, I mentioned that my new sum is getting assigned, my current sum is getting assigned as new sum, right? When I'm calling it, right? So basically what I'm going to be doing is basically I'm going to write the left part. So that's root dot left underscore child, right? And then my new sum or my current sum will be new sum, right? So I'll just write new sum and then I'll just pass in the array, whatever it was, right? So this is calling the left part, right? I'll again pass the same stuff, but this time I'll be passing to the right child, right? I'm going to be recursively calling the right child, as simple as that. Again, this should be new sum and this should be the array, whatever the array is getting filled or recursively getting computed, right? As simple as that. And I hope we are good to go with the execution. Maybe like I can try to print this to see if we are on the safer side. So I'll just write Python, whatever the file name is, branch. I'll just write it like this. And it's saying that list object is not callable. Let's see. We can fix this, right? So answer is get answer tree root. Okay, that's not an issue. Branch sum output root dot left child new sum branch sum output. Okay, my bad. So I can kind of see here that my function name is branch sum compute, right? So up here, I have not written that, right? So I have written the array name by mistake. So this should be branch sum compute, right? And again, this should be branch sum compute. Oh, my bad. So this should be compute, right? As simple as that. Let's see if we are on the right page again. So I'll just clear this and I'll execute. And we can see that we have got that sweet answer, right? 15, 16, 8, 10, and 11. And that's what we were expecting I mean, that's what was expected from the interviewer's end. So that's what we are getting here, right? 15, 16, 8, 10, and 11, right? 15, 16, 8, 10, and 11. What if he tries to kind of trick the question here, right? It's not really a trick. You can kind of figure out what he or she is trying to say. What if it is said that you have to print the branch sums from the right to the left part, right? So what you can do is like simply reverse the output array, right? So on reversing, you will get 11, 10, 8, 16, and 15, right? As simple as that. But what if he says that you're not allowed to reverse the array, right? So reversing in Python is quite simple. It's just writing this and you can kind of reverse that, right? But what if it's restricted that you don't have to reverse here? Again, you have to be familiarized with the concept of recursion. So what you have to be doing is recursively call the right part first, right? So recursively call the right part first and then the left child, okay? So what I'm doing here is recursively calling the right child first and then the left child, right? And the answer is not going to differ at all. Only the output will be in the reversed manner, right? So I'll just clear everything, or maybe like I can just execute here. And you can see here that we have the output in the reversed order fashion, right? This was the output when I reverse the array. And this was the output when I'm not reversing the array, but I'm changing the recursive call fashion, right? So I'm calling the right child first and then the left child. If I call the left child first and then the right child, then this is the output. And I hope the video makes sense. And let's discuss a little about the time complexity, right? And you can maybe pause the video and figure out what the time complexity might be. Well, I can leave that up to you, but I can on an overview, I'll give you one thing, that time complexity, right? So time complexity for this is basically big O of n, right? So big O is basically the worst case time complexity. And the space complexity is kind of interesting here, right? Space complexity is a little interesting here. You might be saying that we have a space of basically 15, 16, 8 and something else, right? So for example, if the tree was looking like this, right? 1, 2, 3, 4, 5, 6 and then 7, right? So if the tree was looking like this, right? So how many space will my output array consist of? 1, 2, 3 and 4, right? So these are the mainly 4 basically space allotment which will be done to the array, right? So this is the output array. Now you can see here that at any point of a time, that's a mathematical proof. You can kind of search up Google, right? So at any point of a time, if it's a full tree, right, a full binary tree here, then in that case, we will have a space of roughly n by 2. Why? See, up here, 4, 5, 6 and 7. How many there are? 4. How many nodes are there? 1, 2, 3, 4, 5, 6, 7. So 7 by 2 is roughly 3.5, right? And I'm utilizing 4 space, right? So that's roughly n by 2 space. Okay, so that's roughly n by 2 space. And again, if you add up the recursion call stack space, right? So all of them kind of sums up to be big O of n. So again, up here, even if you like consider n by 2 here, right? Or maybe like I'll just draw a bigger tree just to give you one example, one more small example. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. And there is a lot of arrow works to do here. I'll just quickly do that. 4, 8, 5, 10, 11, 6, 13. So what will be the size of the output array, right? Let's just figure out. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, right? So this is the output array size. How many elements are there? Let's just count like in a naive way, right? I know for a fact there are 16 elements or 15, 16 elements, but let's just count it like that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 elements. So let's suppose n is 15. What is the size of the output array? Size is basically 8. So is 8 not roughly equal to 15 by 2, which is n by 2, right? So you can say that space complexity is big O is n by 2, right? So n by 2 or n by 3 in terms of big O is basically n, right? Even if you write maybe like n plus n by 2, that's big O of n on a whole another level. So my space complexity up here is also big O of n. right? And if you want more explanation, well, I'm going to be leaving up that explanation to you. You can kind of Google that up and then search up for it, right? You can kind of also search up why time complexity for this code is big O of n, right, after writing the code. So I hope the video was helpful, and maybe we can meet in the next video with